Hey, Algebra 2, Lesson 28. Last lesson before a quiz, but not time for an assessment yet. Newton's law of cooling revisited. We say revisited because we actually touch on Newton's law of cooling for the first time in Algebra 1. But in Algebra 1, we don't learn how to solve for the exponent. Here, we're learning how to solve for the exponent, so that's why we're doing it again. Okay, first of all, Newton's law of cooling is used to model the temperature of an object placed in an environment of a different temperature. The temperature of the object T hours after being placed in the new environment is modeled by the formula. Here we see that T of T is the temperature of the object after a time of T hours has elapsed. T sub A is the ambient temperature, the temperature of the surroundings, assumed to be constant and not impacted by the cooling process. T sub 0 minus T sub A, that would be T sub 0 is the initial temperature of the object, and then subtract the ambient temperature. K is the decay constant. A lot of times we have to solve for K, find the decay constant, and one of our problem set problems has us do that. So that's what we have. Is there anything else I need to tell you? Let's look. E isn't a variable. It's the Euler's constant, about 2.718. K is the decay constant. And basically, we need to know that if we put an object, into a cooler area, we're going to experience decay because we have to get colder, right? If we put an object into a warmer area, I should use a red pen, it's growth because the object will get warmer, right? All right, let's look at our first modeling exercise. I always thought these were sort of fun because they can be like real-world problems in a neat kind of way. This first one is a crime scene investigator. They're called to the scene of a crime where a dead body has been found. He arrives at the scene and measures the temperature of the dead body at 9:30 p.m. to be 78.3 degrees Fahrenheit. He checks the thermostat and determines that the temperature of the room has been kept at 74 degrees. An hour later, the investigator measures the temperature of the body again. It is now 67.8 degrees Fahrenheit. He assumes that the initial temperature of the body was 98.6, which is normal body temperature. Using this data, the crime scene investigator proceeds to calculate the time of death. According to the data he collected, what time did the person die? Can we find the time of death using only the temperature measured at 9:30 p.m.? Well, no. We have two unknowns here. We don't know our decay constant, K, our decay constant, and we don't know our time. So they're both unknown. We need K in order to find T. So because we have two unknowns, we need two equations. So to set up our two equations, we're going to evaluate one at our first time and another at our second time. This will help us get two equations so that we can solve for our decay constant and then use our decay constant to solve for our time. So T1 represents the elapsed time of death until 9:30 when the first measurement was taken, and then T2 represents the elapsed time of death the elapsed time between the time of death, the elapsed time between the time of death until 10:30. Let me rewrite that first one. The elapsed time of death. Oh, too many zeros there. Goodness. Until 9:30, the elapsed time of death until 10:30 when the second measurement was taken. So really, T2 equals T1 plus 1 because it was 1 hour in between, right? So let's write our equations. So temperature evaluated at T1 is 74, which is the ambient temperature, plus 98.6, which was the original temperature of the body, minus 74 degrees. E to the negative KT. Then the second equation is ambient temperature plus 98.6 minus 74 e to the negative KT. Here we have T1 and there we have T2. All right? I'm going to write these down. I'm going to grab them for a new slide so I can start messing with them just a little bit, okay? So I'm going to copy and paste those to a new slide. So write them down. I'll be right back. So you remember we said that T2 equals T1 plus 1, right? Yep, T1 plus 1. We also know a few things. The temperature at T1 is 78.3 and the temperature at T2 was 76.8. So let's do a little substituting. I'm going to take these two values and substitute them up here. So we have 78.3 equals 74 plus 98.6 minus 74 e to the negative KT1. And that equals 74 plus 98.6 minus 74. And here I'm going to substitute T2 for T1 plus 1. Cool? All right, so I've got a system of equations because when we have two unknowns, we need two equations so that we can solve for them. Right? Right. So at this point, we need to combine the two equations in some way using the method of substitution or elimination. When you have more than one equation with more than one variable, unknown variable, then you have to take those two equations, combine them in a way to eliminate one of the variables that we can solve for both of them. So our goal is to eliminate one of the variables. I can't subtract or add as we usually would with variables like x and y when we just have linear equations because these are in the exponent spot. So subtraction is not going to help at all. So what are we going to do? The multiplication property will help. So multiplication is multiplication or division. So we're going to use this property to divide everything to solve. So first of all, let me take these equations and move the 74 to the left side of the equal sign. So I'm going to have this equation. If I subtract 74 from both sides, I have 4.3 equals, simplify this, 98.6 minus 74 is 24.6 e to the negative kt. That's T1. And then I have 2.8 equals 24.6 e to the negative k T1 plus 1. Cool? So we're going to use that multiplication property of equality. We're actually going to divide the first equation by the second equation. I know you probably haven't done that before, but I'm going to divide 4.3 by 2.8 and 24.6 by 24.6 and the remaining stuff, okay? Watch. It'll be awesome. New slide. This is actually part C. Find the value of the decay constant. So I told you I was going to divide them both. And what I'm really doing here is 24.6 e to the negative kt over 24.6 e to the negative k t1 plus 1. All right, those cancel out. I'm left with 4.3 over 2.8 equals, this is the magic part, e to the negative k t1 plus k t1 plus 1. Remember, when you have this in the denominator, to get it in the numerator, it becomes a positive exponent, right? One step further, this right here, I've got negative k t1 plus k t1 plus k. I just distributed, right? And these cancel out. It's magic! 4.3 over 2.8 equals e to the k. Take the log of both sides. You can take natural log or log log, doesn't matter to me. Oh gosh, mistake. Sorry. 2.8 equals k. Oh, I'm taking the natural log on this one. I forgot I had an e. Equals k log e. Because this is 1. So log of 4.3 over 2.8 equals k. So k is approximately 0.429. Yay! We found one of our variables. That's fantastic. Okay, now we know we can find the time of death. So we can take either equation, right? I'm going to take the one that just has the kt in it, not the kt plus 1. My constant is negative 0.429, which we just solved. Divide both sides by 24.6. Now I can do natural log of 4.3 over 24.6 equals, the exponent goes in the beginning, 429t1 log e, which is 1. Divide both sides by 4.29, 0.429, I said that wrong, didn't I? And I have t1 equals 4.0656. So about 4 hours before 9:30 is when that poor soul died. So approximately 5:30 p.m. Isn't that cool? I thought that was pretty cool. Alright, a pot of tea is heated up to 90 degrees C. A cup of tea is poured into a mug and taken outside where the temperature is 18 degrees C. After 2 minutes, the temperature of the cup is approximately 65. So, ambient, taken outside, there's our ambient temperature, initial temperature, and end temperature, right? Determine the value of the decay constant K. So if we look, the temperature after 2 minutes is 65 equals our initial temperature, ambient temperature plus initial minus ambient, e to the negative k times t. Pretty cool, huh? So subtract 18 from both sides. I get 47 equals 90 minus 18. I should be able to do it in my head. 72e to the negative k2. All right, if we take the log of both sides, I have that log of 47 over 72 equals log of e, which is 1, times negative 2 over k. So log 47 divide 72. I have negative 0.4265 divided by negative 2 gives me write it all out. So k equals 0.213. Cool? I could say 2.33, That would work too. Write a function for the temperature of the tea in the mug, T in degrees Celsius as a function of time. So your function time, 18 plus 72 e to the negative 0.2133 t is my function. Cool, that wasn't so bad. Now it says graph the function t. Let me do that for you real quick. You can just put that equation into Desmos or into your calculator, hit graph, it's awesome. Now question D says use the graph of T to describe how the temperature decreases over time. We're starting out at 90 degrees, and if you see, it decreases super fast and then it levels out as it reaches ambient temperature. That's how this works. That is what Newton's law of cooling really refers to. Ambient temperature was 18 degrees C, and I think 10, so that's about 10 degrees. So 18 really is just below 20 with how the graph is until it reaches ambient, but it goes super fast and then it levels out. Let's see, I'd say about 25 minutes is where it really reaches ambient temperature. What else can I tell you? That's it. Use properties of exponents to rewrite the temperature function in the form T of T equals 18 plus 72, 1 plus R to the T. That's an R. Okay, no big deal here. I have 18 plus 72E to the negative 0.213 t. Now you have to do this with your problem set, so let's make sure we remember how to do this. 18 plus 72, and I'm just going to take this, because those are numbers, I can actually calculate this. And that leaves me with 18 plus 72. If I calculate that right there, I get 0.8082. Do this multiplication, I have 18 plus, actually don't do that multiplication, my bad. You're going to just mess with this a little bit, I'm sorry. It's the same as 1 minus, so we take this right here and we do 1 minus 0.8082 and we get 0.1918. And that right there is our function as far as finding that rate of decay. That was fun. Next, in lesson 26, we saw that the value of R represents the percent change of a quantity that is changing according to an exponential function. Right there. Describe what R represents in the constant context of cooling T. R was 0.1918, because right here we get 1 minus 0.1918, and that just means that our rate is decreasing by 19.18% each minute. Right? If it were a plus, if our value was bigger than 1, it would be, your temperature would be increasing, but that's not the case when you put a hot cup of tea in cold weather. As more time elapses, what temperature does the tea approach? It approaches 18 degrees C because that's the ambient temperature. Within the context of the problem, this makes sense because the outside temperature is 18 degrees, so your hot tea, just like when I was showing you in the graph, starts out hot and then it cools until it reaches your ambient temperature of 18 degrees. It can't go below 18 degrees because that's the temperature of the atmosphere. You would have to take away some energy, do something to the tea, drop an ice cube in it to get it below 18 degrees C. Let's see. So when the tea reaches 18 degrees C, it stops cooling. As the temperature goes to infinity, as time goes to infinity, your temperature goes to 18 degrees. Let's try one more. Two thermometers are sitting in a room that is 22 degrees Celsius. When each thermometer reads 22 degrees Celsius, the thermometers are placed in two different ovens. Data for the temperatures T1 and T2 of these thermometers in minutes after being placed in the oven is provided below. So thermometer 1 is given to you in a table, and thermometer 2 is given to you in a graph. The first question says, do the table and graph given for each thermometer support the statement that Newton's law of cooling also applies when the surrounding temperature is warmer? Explain. Yeah. If I look at the graph shows a reflected exponential curve. I reflected it over the x-axis, which means that it's exponential, but my temperature is increasing because my ambient temperature around the thermometer is hotter than what the thermometer was at. I increase rapidly at first, and then I level out, so we can actually tell the temperature at what the oven is, because that's what I'm leveling out at. What else can I tell you? I think that's it. The last example we had, our temperature cooled, and it leveled out with the ambient temperature of the air, right? Question B says, which thermometer was placed in a hotter oven? Well, as time goes on, it looks like the thermometer 1 is leveling out at 176 or above, but we hit 173, 175, 176. We're getting pretty close to our ambient temperature because we've leveled off. This one, we go fast and then we level off, and it looks like we're around 225 degrees Celsius. So thermometer 2 is my hotter oven, right? Yeah. Let's look at part C, and we can come up with some equations. Using a generic decay constant K without finding its value, write an equation for each thermometer expressing the temperature as a function of time. So our first one, thermometer 1, as a function of time would be, so we have the ambient temperature of the oven, initial temperature of the object minus the ambient e to the negative kt. That would be our first thermometer. Our second thermometer, as a function of time, would be, this is about, let's see, what are we going at? 2 or 5, 10, 15, nope, 10, 20, 30, 40, 50. We're at 250, 230, plus our initial temperature minus ambient e to the negative kt. So that right there is question C. Thermometer 1 would be ambient temperature. We're just assuming that we're leveling off. Initial temperature minus ambient e to the negative kt. And here we have ambient, assuming where we level off, initial minus ambient e to the negative kt. Okay, we already answered that. So D, how do the equations differ when the surrounding temperature is warmer than the object rather than cooler than the object? In the case where we are placing a cool object into a warmer space, like these thermometers, the coefficient in front of the exponential expression is negative. We have, in these cases, 22 minus 176 or 22 minus 230. Okay, this part is negative, which is different rather than positive. Okay, we're actually, it's negative versus positive. And then question E, how do the graphs differ when the surrounding temperature is warmer than the object rather than cooler as the previous examples? So our warmer graphs, we have the exponential function that looks like this, and we're leveling off at a temperature. Cooler, oh goodness, that's awful. Our graphs look like that. Cool. That's it for today. I had a lot of fun with this problem set. I hope you do too. Good job.